Good morning, good morning, good morning, and welcome to Euclid's Elements Proposition 1. We're finally there. Okay, as you can see, I had to do a little bit of prep today just to have a few of the pieces we want in place, but this is going to work. Okay, so we are finally starting on Proposition 1. That is Euclid's first proposition. We're actually going to prove something. These are the proofs that I've been talking about. Euclid calls them his propositions. Okay, so actually, you know what? Let's just clarify something. This is Propositions Book 1. There are multiple ones, but we're going to go with Book 1, Proposition 1. Okay. Proposition 1 is as follows. He's going to prove that he can, on a given finite straight line, to construct an equilateral triangle. Okay? That is the goal. That's Proposition 1. That's what we're going to try to prove that you can do. That you can construct an equalateral triangle on a straight line that you know 100% will be an equilateral triangle, which is cooler than it sounds. Trust me on this one. Okay, so what we're going to do here is a straight line. I'm going to put it sort of here-ish. That should work. Okay, I'll put it here. Okay, so I'm just going to grab one of these little headers and cheat this here. Copy that thing, drop it in here. I'm going to drop my line down a little bit further, but I think that'll be okay. Let's put it right in the center, see if I can. Come on, PowerPoint, tell me where the center is. And it doesn't want to. Okay, that's fine. So, what are we doing here? First off, we're getting rid of this extra slide. Okay, so what we're doing here is the first thing Euclid says is let AB be the given finite straight line. Be the given finite straight line. That's okay. That's pretty straightforward. So we're going to call this line here AB. Let's go ahead and give it some. There we go. I'm going to call this we label lines for their extremities. You pretty much label everything for an extremity, I think, except for maybe angles. That's certainly so I can get it all lined up. That'd be kind of fun. There we go. Except this isn't an A, that's B. Okay, so the 2 points at the end that are the extremities of the line are A and B. So this is line AB, except for the A and the B seem really low. Let's get those a little bit closer to the line there. I like that better. Okay, so there's line AB. So that's the first thing we have to do. Done. Now what I'm going to do here is I'm just going to copy this slide and get a second. He says, thus, it is required. Actually, I don't think I would read this one. Okay, so he say, thus it is required to construct an equilateral line on an equilateral triangle on line AB. So he wants us to construct an equilateral triangle on this line. All right. The next thing he says to do is with center A and distance AB, let the circle BCD be described. Okay, so make a circle and we'll call it BCD with its center at A. All right, so that's straightforward. And I happen to have right here, let's go ahead and change the color here. I happen to have right here a circle who is just the right size. That was the prep I did ahead of time. So I'm going to drop my circle in here, and we're going to make sure that it is, there we go, center is A, that's B. So now we will call this circle AB, and let's just BCD. I'll go ahead and just put a D in over here, just so you know what circle we're talking about. There we go. I'll call this D, and I'm foreshadowing here, but I'm going to go ahead and just to make my own life easier, we'll put the C kind of up here-ish. I have to move it again a little bit, but that's not too bad. All right, so we did the thing. So we did check. We have now made a circle with its center. Oh, it's just off. Whose center is A, and okay, center is A, and whose and we'll call it circle BCD, and it has the radius AB. So far, so good. Okay. All right. The next thing we're supposed to do is we're going to duplicate this again, because I don't want to lose our illustration as we get it, but we're doing a new step here. And now he says, again, with center B and distance BA, which of course is the same as AB, let the circle ACE be described. Now, I didn't say at the beginning, but remember at the end of our last lesson, I said you might want to bring a compass and a piece of paper with you. And here's why. Because what you can do now is, using that compass and piece of paper, you can actually go through and do these assignments do these proofs as we go through them. So actually, if you want to go back and draw yourself a finite straight line on the paper, then use your compass to draw a circle with that finite line as its radius and point A as its center. Now we're going to do another circle with the same radius, but with B as the center and A as the edge. So they're going to overlap. I'm going to take the exact same circle so you know that I'm working with the same circle. And this time we're going to do it this way. Boom. Right? Same thing is going on, but now A is the center. Oh, I'm going to move over just a tad bit. Boom. All right. Now A is on the edge of the circle and B is at the center of the circle. And you see how that works sort of nicely. See what's going on here. Okay. So we did that. Check. We have now got two overlapping circles. I'm going to go ahead and move C to this point where they happen to meet, because I think that's a neat point. And since we are now actually we're going to call this circle ACE, because it also has the point C, right? C is the point where they meet. So let's call this E, and now we have circle ACE. It's this one right here, ACE and BCD. Those are our two circles. All right, allergy season. Okay. Let's copy the slide again, and here we go. Now, what is the next thing that Euclid wants us to do? He says, and from point C, in which the circles cut one another, to the points AB, let the straight lines CA and CB be joined. So let's write that out. And from the point C, in which the circles cut one another, see where they intersect with each other, that's what he means by cut one another, to the points A and B, let the straight lines CA and CB be joined. Okay, so we can do that. So all he says is draw straight lines from C to A and a straight line from C to B. So let's go ahead and do that. And again, you can take your compass and do that as well. So we will take our shapes, our straight line tool, and we will pop it right here at where the two lines intersect each other. And there we go. Join that up and paint it black. And then let's do another one. I don't have to put letters on because they already have letters since I'm drawing from points to points. Point C to point B. I think I didn't quite join this up to the point. There we go. To B. And there we go. And look at that. We now have, so we have CA, which just drew, and we have CB, which we just drew. All right. Now, we've actually done it, but Euclid wants to make sure we understand why and how we've done it. So let's go ahead and duplicate our slide again and erase this and see what Euclid has to say. He says, now, since the point A is the center of the circle CDB, center of circle CDB, AC is equal to AB. All right, we know that AC and AB are equal because both of them are at the edges of circle DCB, right? Both of them are circles at the center. Both of them are the edges, or the boundaries of that circle. And since A is at the center, and that's the property of circles, is that all lines drawn from the center to the edge are always the same length, we know that AC is the same length as AB. So good? All right, cool. So we know that. So we know, in terms of equilateral triangle, we've just proved that line AC and line AB are equal. That's an important aspect of our rules for equilateral triangles. I'm going to pause here for just a second. I pause. You probably just saw me jump there, but to bring in, so here are our definitions, the definitions of Euclid's elements. And if we go down here, you will remember that at one point we defined an equilateral triangle. Here it is. All right. So if we go back to our definition of equilateral triangle, an equilateral triangle is that which has its three sides equal. So A, C, and B. If AC is equal to AB is equal to CB, that's an equilateral triangle. That's what we're working with. That's what we're trying to prove. That's just an important thing to remember for what we're doing here. So we haven't proved it quite yet, but we have proved that AB and AC are equal. So these two sides we know are equal. All right. I think you can probably guess what's coming, but let's do this properly. So let's duplicate our slide again and follow Euclid's argument. Again, he says, since the point B is the center of the circle CAE, BC is equal to BA. I think I have an extra space going on. All right, so we know that BC is equal to BA because that line is, B is the center of the circle, and C and A both lie on the boundary of the circle. So BC has to equal BA. So CA is equal to AB, and CB is equal to BA. So far, we're almost there, but Euclid is going to be super thorough, and I hope we can learn to appreciate his thoroughness, because he wants to make sure that we completely and utterly understand why a thing is proved, and when it is proved, and when it's actually not quite yet proved, even though it feels almost proved. So let's duplicate our slide and see what else he has to say. So he says, but, there we go. CA was also proved equal to AB. CA is equal to AB. Right? Remember that? CA is equal to AB. We know that. He's just reminding us of it. I actually said it in the last slide. We're going to have a lot of writing here. Therefore, here's finishing up his argument. Each of the straight lines CA, CB is equal to AB. And the things which are equal to the same thing are also equal to one another. Remember, that was one of our common notions. Let's make all this writing a little bit smaller so it can fit there. All right, there we go. In fact, that was, which common notion was that one? Let me look it up here for us real quick. That should be under, here we go. Is this the right? Yep, common notions. Things that are equal. It's the same thing. Common notion number one. All right, so common notion number one says that things that are equal to each other, to the same thing, are equal to each other, and we just proved that CA is equal to CB and is equal to AB. So these things are all equal to each other. Therefore, need a little more space here. Boom. Therefore, CA is also equal to CB. CA has to be equal to CB because both of them are equal to AB. Right? Does that make sense? CA and CB are equal because both of them are equal to AB. Things that are equal to each other. And finally, therefore, and I'm going to put this one in bold because this is our big final, we have done it now. Therefore, the three straight lines CA, AB, BC are equal to one another. And that, as we all know, is the definition of an equilateral triangle, right? But we'll go ahead and finish it up. Therefore, I know a second therefore, but it's okay. Therefore, the triangle ABC is equilateral, and it has been constructed on the given finite straight line AB, which is what we were asked to do. All right? So he did it, and he proved that he had done it, and he proved that the thing he had done was making an equilateral triangle. We've done it. That is the first proof. You can go back and see it, and if you got any questions, of course, you can ask me, but you need to make sure that you are satisfied that we know for 100% that triangle ABC is equilateral, and I did it without using the equilateral drawing tool or anything. I just drew it. All right. Have a good one.